Okay, moving on. We're going to cover next chapter 10 and 11 from our textbook. This will be reinforcement learning control, or learning reinforcement learning control with approximation. Some to-dos, please be sure to be on top of your assignments. You should be already submitted or in the process of submitting your implementation of tabular Q-learning, SARSA, Q-learning with approximation. Please be sure to complete the deep neural network quiz on Canvas by the deadline. And you should be working on your literature survey for the course project at this point of time. So today we're going to discuss temporal TD methods with function approximation, where we use the approximated value to learn new policy or optimized policies on top of the current policy. So far, we saw how to use approximation of state or action values, V or Q values, to learn action or state values for a given policy, on a given policy. This is on-policy learning. And we saw how to utilize deep neural networks as function approximators for these cases. Today, we're going to also learn approximation of state or action values for a given policy. So we'll also do on-policy approximation, but we're going to use the values that we learn in order to update our policy towards hopefully a better policy, right? So we're going to solve control problem, or we're actually trying to learn optimized policies. We're going to also discuss off-policy learning, that is following some behavioral policy and attempting to learn some target policy. Pi, usually we target pi star, of course. Okay, so first of all, I'd like to discuss on-policy episodic semi-gradient control. So these would be a simple extension over the semi-gradient prediction methods that we previously covered, right? That were only about learning state or action values for a given policy. But now, as I said before, we would like to extend those to control problem. So what we actually want to do is to use the approximation function in order to derive a policy, hopefully a better policy. So we'll mainly focus on approximating Q values instead of state values, which we saw previously, because, well, Q values also help us to define an optimized policy, right? A policy that follows the maximal actions that maximize the Q values. And of course, we'll have to, as before, we'll have to inject sufficient exploration, so we'll combine that with an epsilon greedy or a softmax function in order to ensure sufficient exploration. So this is the pseudocode for episodic semi-gradient SARSA for estimating Q star for learning the optimal policy. So you can see that the main difference here is that for now we also include the control portion. We update the action selection process to be a function of our current Q estimations, with, of course, some injection of some noise for exploration. And as before, we update our approximation, our Q approximation, using gradient descent method, right, that are based on the temporal difference error. So R plus gamma Q in the next state minus the current Q estimation for the current state. Okay, this is the TD error, if you remember. Okay, so let's look at an example of how this works in practice. So for this example, we're going to use the mountain car domain. We have a small car that needs to drive up the mountain to the flag there at the right side. The problem is that even at full throttle, the car cannot accelerate up the steep slope. So the car needs to move back and forth in order to gain sufficient momentum, and then apply full throttle, and once it's gained sufficient inertia, it can drive up the hill to the goal location. So in some sense, things have to get worse. That is, it needs to go further from the goal before it can actually reach the goal. The reward function in this domain, so first of all, the actions are full throttle forward or full throttle in reverse or zero throttle. So we only have 3 actions. This is a discrete action space. We'll discuss continuous action space later on, but the algorithms that we cover at the moment initially are just require discrete action space. For instance, usually Q-learning requires discrete action space. Later on, we'll see some extension of Q-learning for continuous action spaces, but not at the moment. The reward is -1 for all time steps until the car moves past its goal position. So the optimal policy would be a policy that reaches the goal the flag as quickly as possible, because that is the policy that will result in the optimal, the best possible reward, right? Sum of rewards. So if we'll apply semi-gradient SARSA with a specific type of approximation, but you can look at it as a deep neural network, that's fine. With approximation, we get the following learning trends. So the plots on the right report the negative of the approximated state value. Okay, so the Q values, the negative of the Q values. We start at step 0, so you can see several training steps here, starting at episode 104, after we learned a bit. Oh, sorry, we start at, we have an episode 12 there, over there. Not sure what's the order of these. Never mind. We start at episode 12, episode 104, episode 428, 1000, and then 9000. And you can see over time the Q values are shaped into hopefully the correct position, the correct values. So initially at episode 0, Q values are initialized to 0. The first episode, by the way, takes many steps to complete. So you'll also, if you'll be using this domain, you can test your implementations at home on this domain, and you might see that the first episode takes a lot of time to overcome, because the car is moving mostly random until it reaches the goal, before it learns anything. But what the interesting thing to take from here, or to see here, is that over time, as the training progresses, the Q function, the Q approximation, gets to be better and better, where the max action can be approximated to better and better precision. However, you can see that let's say after 100 episodes, the Q estimation is already fairly accurate. That is, it's mostly sufficient to infer the correct action, although it is still being shaped and better tuned into the correct place. But in order to learn the optimal policy, probably you don't need to train it for 9000 episodes. So let's see how that will perform. So you can see here first of all, for these results, these are 3 different results for 3 different plots for semi-gradient SARSA with approximation. The y-axis is the number of steps per episode, right? So once you have an optimized policy, then the episodes will take less time to complete, right? So lower is better here, or lower means a better policy. And the x-axis is simply the number of episodes. So, and indeed you can see that in about 200 episodes we already reached almost the optimal policy, right? And you can see here the different results for different learning rates. You can see that a learning rate, for instance, of 0.5 learned the fastest in this domain. Okay, so, the question, I forgot to ask the question. So, is there a way for us to speed up the Q value propagation? So we can see that the optimized policy was learned fairly quickly, after about, I would say, 200 episodes. Yet the Q values were still shaped into place. We have not finalized on the full Q values. You can see that, for instance, in step 428, we learned some Q values, but they are still pretty far from our final configuration of Q values, as we can see in episode 9000. And the question is, if we converged on the policy so quickly, let's say after 200 episodes, is there a way for us to expedite the Q learning process? Any idea?
Based on what you've seen, is it just changing the learning rate or just performing more frequent updates?
So the learning rate, let's say that the 0.5 is the best one. Do you remember why Q learning might be slow in some cases, specifically in long horizon or in long horizon with sparse reward settings?
Because the values get propagated slow.
The value gets...
We fix that with n-step
right.
TD learning.
Exactly. Yeah. So you see, VABHAV gets full grade for this topic. Yes, so we saw previously that with n-step propagation, we can speed up, expedite Q learning, TD learning in sparse rewards and long horizon domains. And indeed, we can incorporate this idea here in order to speed up the Q learning in this case. So instead of one-step TD learning, TD0, we do n-step bootstrapping. Right? And this requires, we've seen that before, right? It requires just a small change to the SARSA algorithm. I mean, it requires some bookkeeping, but in essence, the idea is pretty simple. We do an n-step look ahead at each step. Actually, each time we get to a step, we look n steps into the past and then update that state action pair, the one that we saw n-step previously. And then what we do here is just extend this idea to do semi-gradient learning, right? So we train our function approximator. And so now we can see that if we include n-step bootstrapping, we can even learn faster compared to one-step learning. Right up. So this is the same mountain car task as before, and you can see that if we do 8-step bootstrapping, it learns faster than a one-step bootstrap. And here we can see what happens. This is more of an sensitivity analysis. If we choose different values of n and different values of alpha, of the learning rate, you can see that normally with larger n, with more look ahead, more step look aheads, usually a lower alpha is more appropriate, or at least in this domain. And we can see that, by the way, the values that are presented in the bottom plot are the average steps per episode over the first 50 episodes and 100 runs, an average over 100 runs. So these are not training curves, but the final performance in the middle of the training, after 50 episodes, right? But as before, lower is better, and we want to find the setting that provides the best results. And you can see that an intermediate level of bootstrapping, specifically the one with n equals 4, right, the blue one, and an alpha of about, how much is it? 0.8, yeah, resulted in the best performance. But these are hyperparameters that usually needs to be tuned per domain, right? So if you have a specific domain, you might need to run all of these possibilities, these hyperparameter assignments, and see which works best in your domain.